Hello everyone, thanks for coming. Today we are going to do a review of our week 6 lecture for ODEs. So in this week, we talk about the power series methods and how to apply these methods to find the power series solution near a regular singular point. The power series basically assumes that the solution takes the form of a power series, and in this form, because we can differentiate term by term, we can write y double prime y prime in the series form and substitute into the second order ODE. From the initial conditions, we can solve for the first two coefficients a0 and a1, or if the initial conditions are not specified, we leave them arbitrary. For higher order coefficients, we recursively use this ODE to determine the recurrence formula in order to determine the higher order coefficients. So for an ordinary point, the series solution will converge at least within the radius of the convergence of P and Q, that is, the smaller one of their radius of convergence for P and Q. So for ordinary points, basically we simply assume that the solution takes the form of a series function. By the existence as unique theorem, the solution always exists, so everything is fine. However, if the point is a singular point, then things can be more complicated. As a simple case, we consider the Euler's equation. For the Euler's equation, the coefficient in front of y double prime is 0 when x equals to 0. However, you can verify that the singular point x equals to 0 is a regular singular point. So there are three cases. For the initial equation, if we replace y equals to xr and then plug in to get the equation satisfied by r, if the two roots they are not equal to each other, then the general solution is a linear combination of the two fundamental solutions, xr1 plus xr and xr2. If the two roots are the same, then the two fundamental solutions take this form. The first one is xr1, the second one is xr1 ln x. So finally, if the initial equation has two complex roots, then the two solutions is x lambda times cosine mu ln x. This is obtained by using the Euler's equation. As a general solution is a linear combination of those two fundamental solutions. So the Euler's equation is actually the simplest equation where a singular point exists. And actually the singular point is regular. So what is regular? The regular is if we multiply capital Q by x minus x0 and then divided by p of x, then this limit exists. Similarly, if we multiply r by x minus x0 squared and this limit x minus x0 squared r divided by p exists, and analytic, those two functions are analytic at x0, then we call x0 to be a regular singular point. If it is a regular singular point, then we can also use the power series method. We assume that y takes the form of a series expansion, plug that in to get the recurrence formula. If any one of those two functions are not analytic at x0, then we call the singular point to be irregular. So the interpretation for the regular singular point is that Q over P singularity lowers than x minus x0 to the power minus 1, and R over P the singularity lowers than x minus x0 to the power minus 2. So for the regular singular points, we can definitely apply the power methods. We use this Frobenius form, x minus x0 to the power r times a series function to determine r as well as the recurrence formulas. So the roots of the initial equation for the lowest order term determine the qualitative behavior near the singular point x0. If the roots are real and differ by an integer or are equal, there might be one or two independent solutions. However, if the roots are complex, then definitely there are two independent solutions, because we can always get the recurrence formula to determine any of those coefficients for the two fundamental solutions. And complex solutions can be converted to real value solutions by taking real and imaginary parts using the Euler's formula, Euler's equation. And for polynomial coefficients, P, Q, R in front of the second order linear ODE, it is often better to work directly with the original ODE than to expand coefficients into power series, because for polynomials we always have finite many terms. So finally, we do have a theorem that tells us what the solution should be like if the two roots of the initial equation differ by integer or are the same. And we will talk about this in our next week's lecture. Thanks for listening.